Today's show is brought to you by ExpressVPN. Protect your online activity today and find out how you can get 3 months free at tryexpressvpn.com/space. That's tryexpressvpn.com/space for 3 months free with a 1-year package. Visit tryexpressvpn.com/space to learn more.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello again, and thank you for joining us on the podcast known as Space Nuts. My name's Andrew Dunkley, and from the Australian Astronomical Observatory is one Fred Watson, and there is only one. Hello, Fred. I know there are others, but you're the only one of your kind.
Well, that's probably true. I'm sure I've told you before that I once got an email from somebody called Fred Watson, and I completely ignored it because I just thought I'd accidentally sent it to myself. It turned out it was
just a great story.
He was trying to email everybody in the, everybody with the name Fred Watson. So I don't know whether it succeeded, but that's all right.
Way too much spare time, really.
It does sound that's
well,
right.
Actually, when I Google myself, which I don't do, I have actually, but I think everyone does. But when I once Googled myself, it brought up the Australian rules footballer named Andrew Dunkley from Tasmania because he played for the Sydney Swans. So as much as I try, I still can't be the most famous Andrew Dunkley. I'm sorry, it's just not possible. Now, today, Fred, we're going to be talking about the Michigan incident, which happened last week. Stirred a few people up too, not the least of which was an issue with the United States Geological Survey tweeting the incident and freaking people out. Not as bad as Hawaii. We also have a question from young Clayton in Texas, which it's a good question. Fact or fantasy, we will find out regarding black holes, Clayton. And Hubble in the news again in regard to a distant galaxy that's been discovered, and it's taken a few happy snaps. But first, the Michigan incident. Now, let me fill you in, Fred. Apparently on Tuesday night, Michigan time, around 8:10 last week, the sky was almost literally ablaze with a fireball, which was caught by dash cams and all sorts of other cameras all over the place. Created an incredible light show, and it turned night into day ever so briefly. And I suppose we've seen these things before. They're not absolutely uncommon, but they're quite spectacular.
They are. You're right, though, to highlight that they're not totally uncommon. They are, they're certainly striking when you see one. And I guess we would probably see more of them if we weren't all in the evenings sitting huddled around our TVs and our game consoles and our phones and our pads.
Famous story. I missed a tornado once because I was glued to a television set. Seriously, if I'd looked out the window, it would have been there, but
you didn't bother looking.
I missed it.
Oh dear. Well, yes, I think that's probably. I think that happens a lot with fireballs. So what's a fireball? It is a piece of space debris, and it's natural debris, not space junk that we create ourselves. A piece of natural space debris that hits the Earth's atmosphere at pretty high speed. This one in the region of 15 or thereabouts kilometers per second. The speed that it hits the atmosphere at basically vaporizes it very quickly. And if you've got an object that's big enough, maybe the size of a football, that will be, it will be long-lasting enough that it brightens up very, very strongly. And so you do get this curious phenomenon where just very briefly, perhaps for less than a second, the landscape is lit up as bright as day. I've seen several times from Siding Spring Observatory, and it is always worth seeing. It's quite striking. Suddenly the landscape is in daylight, and you think, what? And then, it depends where you're looking in the sky, but you might just catch a trace of this. And sometimes there's a bit of an afterglow as well, with the ionized path through the atmosphere that's still glowing. the trick, though, if you do see one of these things, is to kind of hang around for a few minutes, because somewhere around 5 minutes later, there's a chance that you'll hear the sonic boom. And I've done that myself. A few minutes later, you get this double dull thud, which is the sonic boom from the meteor hitting the atmosphere. Why is it so much later? Because
that was what I was going to ask.
I read your mind. It's because all the action takes place about 90 kilometers above the Earth's surface, and of course 90 kilometers is quite a long way. Yeah. And sound travels at sea level at about a third of a kilometer per second, but up there it's slower, and you get basically you get this delay before the sound hits the ground. That, of course, can be dangerous too, because the famous Chelyabinsk incident, which was in, I think, February 2013, this was a piece of debris much bigger than a football. This was something the size of a house that hit the atmosphere at about 30 kilometers per second. It actually penetrated very deep into the atmosphere before it disintegrated, but some of the bits and pieces did land on the surface. They are called meteorites when they hit the surface. But the sonic boom from that was very dangerous. What happened, as you and I have spoken of before, is that people saw the flash. In this case, it was 30 times brighter than the sun. Yeah. They saw the flash, and all rushed to the windows to find out what it was, because they weren't watching their TVs or whatever.
The shockwave hit them.
The shockwave hit the glass and broke pretty well every window in Chelyabinsk and knocked down a few walls as well. So something like 1,200 people, I think, were wound up having to visit hospital. This one in Michigan was nothing like that. It was a smaller event. We've seen the dash cam footage. It was spectacular. It did the old trick of lighting up the landscape. I haven't heard any reports of sonic booms, but I'm sure there would have been. It basically straddled the southern end of the Great Lakes region in the USA, seen by something like, or reported by something like 355 individuals. So quite a good sighting, and maybe it just came at the right time of day for people to be out and about and see it.
Yes, indeed. Oh, well, a lot of traffic on the big highways over in America, and everyone's got dash cams these days, so quite a bit of footage there. But security cameras picked up the parking lots and things like that lighting up, and you could just see how it was dark, and then it just sort of glowed, and then bright white, and then it tailed off. It was quite spectacular. Yeah. They reckon that the meteor was about 2 meters in diameter.
All right.
And it was coming in at around about 45,000 kilometers or 28,000 miles an hour, which is pretty slick.
It is, that's right.
Yeah, great footage of it.
And there's certainly thinking in this case that this object might have produced debris that made it to the ground, which become meteorites, and of course are free samples of space material. They're very highly prized.
Indeed. One downside, and that's why I referred to it as the Michigan incident, the US Geological Survey in Detroit sent out a tweet confirming the meteor occurred at 8:10 p.m, causing a magnitude 2 earthquake. That kind of freaked people out, because they don't cause earthquakes. It might have had the power of a magnitude 2 earthquake, but it didn't cause an earthquake.
No, that's right.
Phew.
And just one final footnote on fireballs generally. So what's the difference between a meteor and a fireball? It's just a matter of degree. A meteor is what we normally think of as a shooting star, something that whisks across the sky. If it's bright enough, it becomes a fireball, and this definitely was in that regime. It's also worth looking, though, if you ever do see one, just see if you can see any colour in the brilliance of the light that's coming out. Dash cams and things like that are not very good at showing up these subtle colours, but the eyes are pretty good, and often there is a greenish colour to the fireball, and that's caused because the friction of the fireball is exciting oxygen atoms to give off their characteristic green light, which they do when they're excited. It's actually the same reason why the aurora borealis and the aurora australis are predominantly green.
How about that? One final thought. I know we've spent a fair bit of time on this, but how do the Chelyabinsk incident and this one differ from the Tunguska event in the early 1900s?
Yeah, pretty well, only in terms of scale. The Tunguska object was probably about 40 or 50 meters across. As I said, the Chelyabinsk one was about the size of a house, I think 20 meters or thereabouts. So yes, there is a spectrum of sizes in these things, and the tiny ones are the most common, the ones we see as shooting stars. But the bigger ones do exist, and maybe within the next 100 years or so, we might be due for another thing like the Tunguska event. Although it is now, it's getting to the size that about 50 meters, that's getting to the size which we can detect in advance with the flotilla of telescopes that we now have looking at the space exactly for this kind of thing, for asteroids small asteroids or big meteors that might hit the Earth.
Yeah, well, hopefully if that ever happens again, it doesn't happen over a major populated area. But I'm still coming up with questions. How big is too big? I mean, how big does it have to be before it becomes a really significantly dangerous thing?
Yeah, something 50 to 100 meters is dangerous. If it hits a city, it really would devastate the city area. When you go up in size, of course, the devastation increases very rapidly. And the most dangerous ones are ones like more than half a kilometre. Then you're talking about hemispheric devastation. When you get up to a kilometre, you're talking about global effects. And a kilometre is not very big, Andrew. But we believe that NASA has catalogued something like 90% of near-Earth asteroids a kilometre and above. That's based on statistical studies. Of course, there'll be a 10% that you don't know about, and they're the ones to worry about.
Indeed.
Right.
Well, we'll probably talk on this again the next time a major fireball incident happens, but they certainly got a good look at it in Michigan last week. You're listening to Space Nuts. Andrew Dunkley here and Fred Watson. Now, let's take a little break and find out more about our sponsor, ExpressVPN, rated #1 by TechRadar. This is the one I use. I've been using it for a couple of years and I love it. When I joined ExpressVPN, they were brand new to the market, but I read a lot of reviews and did a lot of comparisons. And there was just something about their business model that I particularly liked. And a couple of years down the track, honestly, can't complain. Their interface is very easy to use. Their service is second to none. I've had to contact them a couple of times about certain things that I wanted to do, and they were brilliant. So you may be wondering why I do need a VPN at all. It's all about privacy. Do you really want big tech companies, governments and others knowing what's going on with your online activity? Even if you're having nothing to hide, it just feels downright creepy. I think you'll agree. And governments are getting more and more interested in what you're doing every day. And so, protecting your privacy is what VPN is all about. And how often do you run across websites that you want to get information from only to find that they're geo-blocked? This is becoming an increasing problem, but ExpressVPN solves that problem for you. Now, if you go to our special URL, you'll see quite a list of things this service can help you with, things you may never have thought of before. As I say, it's the one I use, secure, fast, and it just works. So protect yourself online today and find out more about how to get 3 months free at tryexpressvpn.com/space. That's tryexpressvpn.com/space for 3 months free with a 1-year package. Try expressvpn.com/space to learn more, and you'll find the link details in the show notes and on our website. Now, back to the show.
0G, and I feel
Space Nuts.
Now, occasionally, Fred, we get a chance to have a talk about something that the Hubble Space Telescope has achieved, and it's certainly done something pretty spectacular this time around with the discovery of one of the oldest known galaxies so far. And you can learn a lot, I suppose, from something so ancient as this.
That's right. This presents its own problems, of course, because very distant galaxies are very faint and usually appear just as a point of light in Hubble's field of view. But this one has had the benefit of a kind of natural zoom lens, something we call a gravitational lens. And what happens here is that an intervening object, something between ourselves and this very, very distant object, and usually it's a cluster of galaxies, and galaxies are pretty big objects. Yeah. A cluster of galaxies essentially distorts the space around it and turns it into a lens. That gravitational distortion is what Einstein told us happened. We've had countless examples of it happening in practice, so this is very much the stock in trade of astronomers these days, to look for gravitational lenses and look for their potential as natural zoom lenses or natural telephoto lenses to magnify more distant objects beyond the galaxy cluster. And that's what's happened in this case. And this story actually, like several at this time of year, has come from the most recent meeting of the American Astronomical Society. They meet every January. They're meeting this year in Washington, D.C., or they have met. It's the 231st meeting. That's pretty good going. But often at those meetings, you get really interesting scientific news stories, and this is one of them. So what's happened? Well, the Hubble has been used to look at one of these distant objects that has been given a close-up view by virtue of the gravitational lens. So this particular galaxy we are seeing as it was 13.3 billion years ago, which is almost the entire age of the universe. So, as you look further and further out into space, you're looking further and further back in time because of the speed of light, the finite speed of light. In this case, the light-time journey has been, as I said, 13.3 billion years. So when the light left this object, the universe was only 500 million years old. It was, half a billion years after the Big Bang. And it's not that long ago that we would have thought, well, this is not long enough for galaxies to have formed. But we now have a different view of that because we see objects at this sort of distance and at this kind of look-back time, which clearly are galaxies and which certainly have some structure to them. They don't have the neat and tidy appearance of modern galaxies where we've got this kind of grand design spiral structure like our own galaxy, which if we could see it from the outside would be absolutely stunning because of its symmetry. We don't see that in the early ones. They have structure, but it's fairly higgledy-piggledy. However, the theory says that at this very early age, I mean, these are newer theories of how galaxies form. Theory does predict that you might start to see spiral structure in objects seen this long ago or this early in the history of the universe. And that's the nub of this story, that there seems to be in this gravitationally lensed image of this distant galaxy that existed just 500 million years after the origin of the universe, there seems to be structure that really suggests that it does have these spiral arms, rather like ours, but not as neat and tidy. They're much kind of looser wound and have a lot more what you might call roughness to them, because there's obviously a lot of turbulence in these early galaxies. The gas and the dust and the stars are thrown together in a bit of a mishmash without having time to settle down dynamically, which is basically what's happened to our own galaxy. And that's why it looks so good. So a great piece of work. This galaxy in the depths of space, seen, as I said, 500 million years after the Big Bang. This is an obvious target for the next generation of big telescopes. And in particular, the James Webb Space Telescope, which is basically NASA's next big thing in space. It will replace the Hubble. It's due to launch next year, in fact. But galaxies like this, and this one in particular, will be, there'll be targets for not just the James Webb Space Telescope, but the new generation of extremely large ground-based telescopes as well. So we await news from space on these things with great interest.
Yeah, you might be able to clear something up for me, though. What Hubble observed and what that galaxy is like now would be very different. Would that not be the case?
That's right.
Because we're looking at historical light.
We are. However, the idea of a now.
Yes, that's it, isn't it? It's a very loose thing in astronomy terms.
That's right. And in fact, it doesn't really have any meaning when you're talking about one vantage point, because there is no getting around the fact that you are always looking back in time. So, but if you think of what it will be like if you were standing next to that galaxy now, 13.8 billion years after the Big Bang, 13.3 billion years after the light left it that we've now detected. If you imagine yourself standing next to it, yes, it would be quite different. It may have done what we think many galaxies do, which is to accrete or gobble up smaller galaxies. We know our galaxy has grown by this method. And it suggests that perhaps this dim and distant object that we see as a smudge in a Hubble telescope image might now be a very imposing spiral galaxy, with its own retinue of smaller dwarf galaxies, and maybe even planets with living organisms on them. Who knows?
Yeah, well, the more we learn and the more we can take advantage of improving technology, the more we're starting to see commonality throughout the universe, planets, galaxies. And perhaps life is a part of that as well.
We'd like to think so, and that's really what the science of astrobiology is all about. And you and I report on the latest stories in that whenever they come out.
We do. We hope to. Well, if someone beats us to it, we don't really care, but we'll still report on it. This is Space Nuts. Andrew Dunkley here, and Fred Watson from the Australian Astronomical Observatory.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Last but not least, Fred, we have a question from our studio audience. I can hear crickets. But we do have a question from Clayton in Texas, who's emailed us to say, "Hello, Andrew and Fred. Love the show. Big fan, blah, blah, blah." That's what he wrote. Sounds like me. My question concerns black holes. I was recently made aware by a friend that black holes are actually still theoretical. Is this true? If so, why are black holes so often presented as scientific fact? How do scientists know black holes exist if one cannot see them? Because not even light can escape from a black hole. Best of luck to you both. Thanks for a great podcast. Clayton Baker, Texas, USA. Do they exist, Fred?
They do. But look, Clayton's is a great question because it really goes to the heart of what astronomy is all about and what we do. We have to, because we can't go and grab hold of the things that we are investigating in the world of astronomy. Generally speaking, what we have to do is observe what we can, and then build models that rule out any other possibilities, and then say, well, the reason why this is like that is because this, and this are happening. For example, the story we've just been talking about. We know that this smudge in space is not actually a smudge in space. It's a galaxy, because we understand the processes by which the light from it has been magnified and kind of slightly distorted. So with black holes, it is quite right that in a sense they are theoretical entities, because nobody has yet imaged a black hole. Now, that might sound like a daft thing to say, because of course a black hole is by definition black, because its gravitational pull is so strong that nothing, not even light, can escape from it. But we do have ways of imaging black holes, and that it's likely to happen actually in the next 2 or 3 years, because radio astronomers are basically putting together an array of radio telescopes that will be able to detect the radio emission coming not from a black hole but from the region immediately around it, where objects are being sucked in and they're being energized to very high levels, and that makes them emit things like X-rays, but also radio waves. And it may well be that soon we have an image of this swirling disk of material around a black hole that clearly shows the missing bit in the middle, which is what we call the event horizon. That's where the dark blob is that represents the black hole. So that's something that, maybe we'll be able to say then, well, they're clearly no longer theoretical entities. They do exist. But we can already say that, Andrew, because of observations that have already been made. And perhaps the most convincing observations yet of the existence of a black hole, and this is a supermassive black hole. Its dimensions are that it weighs something like 3.6 million times the mass of the sun, so it's a big black hole. Yeah. This one sits at the center of our galaxy, and over the last 20 years or so, astronomers have observed stars which are actually around the black hole. And what you see is these stars all in orbit around nothing.
Yeah.
They're actually orbiting something that is clearly very massive, but there's nothing to see. At least there isn't invisible light or infrared radiation, which is what they used. You can see it in the radio region of the spectrum, and in fact that's how we discovered it. This thing is a radio source. It's called Sagittarius A star. That's its name, and that's how it was first discovered, that there's this object at the center of our galaxy, very precise and pinpointed target in radio waves. But that's not the black hole itself. The radio radiation is coming from this swirling disk of material around it.
So, in short, really, what you're saying is we can see the effects of black holes. We can see the evidence of what they are doing in their surrounding areas, but we can't actually see them.
Yeah, in this case, that's correct. I think we will eventually, and might not be too far down the track, I think we will eventually see black holes. And in fact, that one at the center of the galaxy is the one that everybody's got their eye on, to look at the accretion disk around it, the swirling disk of material. But the point I was going to make about these stars in orbit around Sagittarius A star, which is dark in the visible and infrared region of the spectrum, they are orbiting around something that can only be a black hole. That's the trick, because they're orbiting around an area of space that is particularly compact, but you also know that it has a mass of 3.6 million times the mass of the sun. So it can't be anything else. That's the bottom line. It rules out neutron stars. It rules out star clusters or anything of that sort. It's got to be a black hole. It's the only entity that can demonstrate that kind of gravitational pull. So in that regard, Clayton's question takes on a slightly different complexion, because it is a theoretical entity, but it is the only theoretical entity that could fit the bill. And so in that case, really, we are observing it, in as solid a way as you possibly can.
Yeah, and we're learning more and more about black holes. You and I talked last year about the fact that they were confused as to why there were only two sizes, supermassive or small.
Yes.
And why aren't there any medium ones? And then within about a week, I think they found a medium one. So we're starting to really fill in these gaps, so to speak.
Yeah, that's quite right. But, as I said, Clayton's question is a good one, because it goes to the heart of our science. You could say the same thing about the Big Bang. We are absolutely convinced that the Big Bang existed. We see its afterglow in the sky. We see its effect in that the galaxies are all racing away from one another. But as yet, we cannot see the Big Bang itself, looking back 13.8 billion years. It's possible that in the future, using gravitational waves, we will be able to detect the gravitational crunch of the Big Bang, and that will be a great breakthrough. But at the moment, it remains a theoretical entity, just like the black holes are, but with overwhelming evidence to suggest that they are real.
Indeed. All right. Thank you, Clayton. Great question. And we certainly do encourage people to send us their questions, and we'll do our best to try and put them in a drawer and forget about them. But if we do have to answer them, we will. I just actually found out there's another supermassive black hole much closer to us, Fred. It's called the Australian Taxation Office. So I'm going to get investigated now, aren't I?
Well, you probably will, and serves you right. Throwaway lines like that left alone.
Yeah, it's actually a law in Australia that you don't make jokes about the Australian Taxation Office. So. Oh dear. Fred, as always, thank you so much. It's been a pleasure.
I hope, that next week when we try and speak, you're not locked up somewhere because of making jokes about the ATO. But it's been a pleasure talking to you as well, Andrew, and we'll chat again soon.
Look forward to it. That's Fred Watson from the Australian Astronomical Observatory. And from me, Andrew Dunkley, thank you for joining us on Space Nuts, and we look forward to catching up to you again very, very soon.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Subscribe to the full podcast on iTunes, Audio Boom and Stitcher, or your favourite podcast distributor.
This has been another quality podcast production from Bytes.com.
And the analysis that has been done with the Hubble telescope demonstrates that we are looking back 13.5 billion years. I beg your pardon, let me get the right number. 13.8.
Sorry, Fred. I'm going to stop you.
How are you doing there? I'm disturbed because I can see that
trying not to cough, but
you are in distress. Yeah,
it caught up to me. I just got to get some water.
Get some water and we'll edit this.
I'll keep the recorder going. I can edit it later.
Yeah.
Oh dear.
Poor old Andrew's snuck out of the room. He's disappeared into the ante-room looking for water to quench his insatiable instinct.
It started as a tickle and ended up as a, I don't know what. But anyway, that solves that.
I've given the editor a running commentary on your...
have you? Oh, dear. The wonders of water. I feel better now.
Yeah. So I was distracted by your obvious distress and actually got the wrong number there. So I'm going to repeat what I said.
Okay.
We okay just to pick it up?
Yep, go for it.
Space Nuts.